All right, we're back. Now that you have an understanding of light and how we interpret it, it's time to move on to talk about exactly how we collect all that light to begin with, which is usually telescopes. Let's talk first about the main advantages of using telescopes for astronomical research, and let's talk about them through the groundbreaking work of Galileo. So Galileo had a few major discoveries using his telescope, right? He saw the four largest moons of Jupiter. He noticed faint stars in the Milky Way that aren't visible without a telescope. He documented the phases of Venus, and he saw moon craters in pretty good detail. So these accomplishments can be divided really into two main categories that illustrate the advantages of telescope use. So first is the improved light gathering power or improved magnitude. So this is illustrated by Galileo's observation of the moons of Jupiter and his observations of faint Milky Way stars. So neither of these things were visible without a telescope. The telescope allows us to gather light to an extent that our eyes cannot. These observations were too faint to be made without it. The second is improved resolution or improved ability to see fine detail. This is illustrated in Galileo's documentation of the phases of Venus and the craters of the moon. So we can see the moon and Venus without a telescope, but we couldn't see the details that Galileo did with his telescope. Over time, there have been observational improvements, right? So first we had a quite small telescope and pointed it at the sky, but over time we improved the optics and made telescopes larger, which really improved what we could see. Eventually, we kind of stuck a camera onto the eyepiece of the telescope and we made that camera digital. Maybe we attached some instruments that could see in other wavelengths, and eventually we sent telescopes into space. A lot of these things, were happening kind of at the same time, right? It's an iterative process, constantly making improvements, right? Improving the optics and figuring out different ways to improve our images. So let's talk a little more about the advantages of telescopes. And first, let's talk about the increase in light gathering power, or LGP, this ability to see fainter objects. So this has a lot to do with how big the telescope is, right? If we make the diameter of the telescope twice as large, right, the aperture, the hole in it, kind of like this area here, if we make it twice as large, we get 4 times the light gathering power. So when we say telescope size, we mean the aperture, right? The opening where the light comes in. So the aperture of Galileo's telescope was about 2 inches, so maybe about like the length of your thumb, perhaps, right? You can buy kits to make these telescopes today for like 20 bucks. They're pretty inexpensive. For maybe a couple $1,000, you can buy something like this, which is an 8-inch Celestron telescope. The Braille telescope, which was many, many thousands of dollars, it's on the roof of Roger Bacon Hall. This is a 27.5-inch telescope. So you can imagine um, how much different the light gathering power is from a 2-inch telescope to an 8-inch telescope to a 27-inch telescope. The other advantage is the improved resolving power, or the ability to see fine details, right? Resolving power is basically the smallest angle a device can resolve. And the larger the angle, the fuzzier something looks. So the equation that we would use here, it's basically proportional to the wavelength of light you're looking at and the diameter of the aperture. And so this is an example, kind of a cartoon of what we mean by resolved. And so This right here, this would not be a resolved image. It just looks like one. If it's very resolved or just barely resolved, I mean, you can start to see there's actually two things right here, which are very close together. But if we can get a pretty big diameter telescope, we can start to actually split these two objects up. And this is a very well-resolved image. But the larger this angle, the fuzzier an object looks in your eyepiece. The trend in making telescopes more powerful is basically to make them bigger, right? This gives them more light gathering power and more resolving power. But if there are problems with using telescopes, the first is not really the telescope's fault, but it is the weather, right? Atmospheric conditions are not always favorable. Humidity and temperature, even if the sky is clear, affect something called the seeing. Basically, how uh, distorted the objects that you're looking at actually seem. Another problem is light pollution, right? Light pollution is extraneous light, from cities and towns and satellites that really wash out the night sky. And it's getting harder and harder to really get away from. This is a map of the United States um, with its light pollution. Up here, kind of New England, New York area, there's a lot of light pollution. Out west, there's a little bit less, but you can see how it would be hard to kind of get away from like lights of cities and how that would be harmful to astronomy with these big telescopes. There are also some limitations in telescope design. There are basically two types of telescopes, kind of general types. There's a refractor and a Newtonian reflector telescope. A refracting telescope uses a lens to focus light. So here's a little bit more blurry than I thought it was going to be, but this is the lens right here. This is the eyepiece here. Um, Light comes in this way, and the lens focuses the light and comes through the eyepiece here. So the lens, of course, is like a thicker piece of glass. It needs to be incredibly precise and really polished on both sides, right? It needs to be pretty much perfect. One of the issues with refracting telescopes is something called chromatic aberration, and it's illustrated right here in this image. So different colors of light, different frequencies of light focus at different points when that light goes through the lens. So there are things you can do to kind of mitigate this, but it still causes colors of light to be offset a little bit from each other. So we have here, remember, we have maybe light as a continuous spectrum coming in, but when it goes through the lens, each wavelength of light, it kind of bends just a little bit differently, a little bit different angles. And so when it comes up, you can see there the light is separated and actually really focusing at different spots. So the red light focuses here, the green focuses here, the blue focuses here. So you can see why that would be a problem with astronomical observations. A reflector, on the other hand, uses curved mirrors to focus light. So here's what we have here. So light comes in from this direction here. There's a curved mirror at the bottom. The light bounces back, comes up here to a secondary mirror, and bounces through an eyepiece. It's a little bit longer, a little more, well, just slightly more complicated, but with the mirrors have to also be extremely precise, but you only need to polish really one side of it, and it doesn't cause the chromatic aberration that these lenses cause in refracting telescopes. Okay, so right here, I think this is the Yerkes telescope. I think I'm pronouncing that right. So this, I believe, is the largest refracting telescope ever built. You can see how huge it is. This is just a guy standing right here, and this is the telescope. It's a 40-inch telescope at the Yerkes Observatory at the University of Chicago. And this is an example of Herschel's reflecting telescope, which is also absolutely huge. So you can see just from these here that um, building very large telescopes is actually a huge engineering problem, and it's very expensive. I will note that it's also very hard to make really large refracting telescopes, especially making them as big as you can make reflecting telescopes because of its use of a lens, right? So this is just a chunk of glass and it can be extremely heavy. So mirrors can get heavy too, but not really as much as a chunk of glass. So just the idea that you have to have like a very large, thick piece of glass makes those things very heavy, very hard to move. There have been advances though in telescope design, like those were kind of two basic types, but they have been improved on, especially reflecting telescopes have been improved upon. A popular design for a reflector is called a Cassegrain reflector. So we have like a classic Newtonian reflector right here and the Cassegrain over here. So again, the Newtonian reflector, light comes in, bounces off this primary mirror, then hits the secondary mirror, which is bounced into the eyepiece. It's actually quite a simple design. The Cassegrain reflector is a little bit different. So light comes in here and bounces off a mirror, but there's a hole in the mirror right here. But the light bounces off the mirror, the primary mirror, up to the secondary mirror, and then the eyepiece is actually at the back of the telescope. It goes through the hole in the mirror, out the eyepiece in the back. So the benefit of something like this is that it has a shorter focal length, which means that you can have a smaller telescope for the aperture. And because it uses a mirror and not a lens, there's no chromatic aberration, just like a normal Newtonian reflector. There have also been advances in mirror technology, and this has been especially important as we've sent telescopes into space, right? We want to save as much rocket fuel as possible. We want our mirrors to be as light and efficient as possible. So we can make very thin floppy mirrors called a floppy mirror. And we can make segmented mirrors. Like this kind of looks like the James Webb Space Telescope might use. So for segmented mirrors, this is very easy. It's like if something happens to one piece of the mirror, you can replace it. If something breaks on the floppy mirror, you have to kind of make a whole new mirror. Also, both the floppy mirrors and the segmented mirrors make adaptive optics possible. So this is kind of just an ability to shape the mirror in a slightly different way, kind of on the fly for each observation, which is actually extremely, extremely useful. There is also a method called interferometry, which is basically adding the signal from different telescopes to effectively get the light gathering power of a much larger telescope. You can basically make a telescope the size of the baseline of the individual parts. And we've also sent telescopes into space, right? This is necessary, remember, to even detect some wavelengths of light. Basically, any wavelength other than optical and radio has to be observed from space, or at least very near space. Here's kind of my favorite examples of space-based telescopes. This was NASA's Great Observatories program. It consisted of these four space-based telescopes. We had the Compton telescope for gamma rays, Spitzer for infrared light, we have Chandra for X-rays, and Hubble, like the very famous Hubble Space Telescope for visible light and ultraviolet light. On the ground, of course, we have some really great radio telescopes. Some of the most famous ones, there's one at Green Bank Observatory in West Virginia. and one at Arecibo Observatory in Puerto Rico, or at least it used to be before basically a hurricane hit it and it really destroyed the telescope, which is really quite a tragedy, right? The Arecibo telescope right here was a really great telescope, a really great radio telescope. Finally, some examples of interferometry is the Atacama Large Millimeter Submillimeter Array in Chile, or ALMA, a much shorter name for that. This is a radio observatory with 66 individual telescopes. So these are the telescopes, these radio dishes, not kind of the lenses that we're used to, but this is how you view in the radio. Another use of interferometry is the Event Horizon Telescope, the EHT, that imaged a black hole for the first time several years ago. So the EHT is another radio telescope where the individual telescopes are placed basically around the world. Like these are the individual radio telescopes that were involved in the Event Horizon Telescope. So effectively, we have a telescope about the size of the Earth, which is wild, right? So these are both really amazing telescopes and are worth looking into a little bit on your own if you're interested. Okay, that's all for this lesson. If you have any questions, shoot me an email, come by my office hours.